Michaela and Ashley, and we're going to go over Theorem 9.5, which says that no permutation in Sn can be expressed both as a product of an even and odd number of transpositions. So for the first proof of this, we're going to take this from a linear algebra perspective. And before we get into the actual proof, let's go over the main idea. So let's say we have sigma equals this. We know that this can be written as a permutation, and that as transpositions it would be written like this. Now, let's say that we have the identity matrix with 3 rows, so I3. The identity matrix would look like that. And now if we apply sigma to the identity matrix, we will get a new matrix. Let's call this matrix C. Where we take the first row and put it in the second place. We take the second row, put it in the third. And we take the third row of the identity matrix and put it in the first row. And so that's our new matrix. So we know that the determinant of all identity matrix is 1. And we know that by switching any 2 rows of the identity matrix, that'll change the sign from positive to negative. So if we had the identity matrix of 2, that would usually be 1 minus 0 because it's this vertical versus this one. But if we switch the 2 rows, then it would be 0, 0, minus 1 times 1, which equals negative 1. So switching any 2 rows changes the sign of the determinant, and each transposition is corresponding with a switch in 2 rows. So if another transposition were to be added, which would be the case if it could be written as even and odd, adding another transposition would cause a switch in the matrix, which would cause the determinant to change from positive to negative, which is impossible because then the determinant of C would have to be 1 and negative 1, and 1 and negative 1 are not equal, so that is impossible. So going on to the actual proof. So we know that SA is isomorphic to SB if A and B have the same cardinality. This means that without loss of generality, we can use the permutation of n rows of the n by n identity matrix In rather than numbers 1 through n. So as we said before, we know that the determinant of the identity matrix is 1, and that interchanging any of its rows would cause a change in the sign. So, if we let C be a matrix obtained by permutation sigma of the rows in, then if C can be obtained from IN by both an even number and an odd number of transpositions, then its determinant would have to be both -1 and 1, which is impossible. And that's a proof using linear algebra.
Okay, so the second version of this proof is very similar, but instead of using matrices, we are using permutations. So let's start by working on an example. Let's use S5, and let's have the permutation where 1 goes to 3, 2 goes to 4, 1 goes to 3, 4 goes to 5, and 5 goes to 2. This can be decomposed into a product of the short cycles, which would be 1, 3, and 2, 4, 5. Now, this has two orbits, and visually you can see it like this, going in this direction, and then 2, 4, 5, going in this direction. Okay. And now let's have the transposition 1, 4. Then the product of the transposition and the permutation is 1, 4 composed by 1, 3, 4, which yields 1 remains at 1, 1 goes to 3, which remains at 3. Then 3 remains at 3, 3 goes to 1, and 1 goes to 4. 4 goes to 5, which remain at 5. And then 5 goes to 2, which remain at 2. And then 2 goes to 4, which then goes to 1, and so we are done. Notice now that we went from 2 orbits into 1 orbit after taking the product. So visually this is now 3, 4, and then 2 going in this direction. And now let's consider the permutation 1, 3, 4, 5, 2. As we see over here, this is 1 orbit. Right? And let's now look at the transposition 3, 2. The transposition have elements that are in the same orbit. And then the product of this is where 1 goes to 3, which goes to 2, and then 2 goes to 1, which remain at 1, and then 3 goes to 4, which remains at 4, and 4 goes to 5, which remain at 5, and then 5 goes to 2, which goes back to 3, and so there we have it. Now notice when the elements of the transposition are in the same orbit, the orbit will split into 2 separate orbits. So now from here to here, we have 1, 2 in 1 orbit, and our other orbit contains 3, 4, and 5. Now let's look at the identity permutation in S5. All identity permutations are where the elements go to itself. So all of the elements are in its own orbit. Now let's take the permutation 1, 3, 2, 4, 5. This has 2 orbits, and we know that all permutations can be composed by its transpositions and the identity permutations. So this can be written as 1, 3, 2, 5, 2, 4. Let's double check to make sure if this is true. 2 and 4 are in separate orbits. So this yields 2, 4, 3, 5. 2 and 4 combine into 1 orbit, as we have seen over here. Okay. And then 2 and 5 are once again in separate orbits, so we will combine the orbits, which now gives us 2, 4, 5, 3. And then lastly, 1 and 3 are in separate orbits, so we combine those. And we see that this is indeed our permutation. Well, our permutation here was composed by 3 transpositions, so this is an odd permutation. And our question is essentially like, can we write this permutation with an even number of transpositions? So let's try adding any other permutation to our permutation. Let's take 4, 5. And we want to see if this is still our permutation. Well, as we see over here, this yields that. So we have 1, 3, 2, 4, 5. And then we have 1 goes to 3, which then remains at 3. And then 2 goes to 4, which goes to 5. And then 5 goes to 2, which remains at 2. And so 4 is now in its own orbit because 4 and 5 were in the same orbit at first, and now they split. And the important thing to note is that when the transposition has elements in the same orbit, it will split into 2 orbits. And then when the transposition has elements in different orbits, it will combine into 1 orbit. Now moving on to our actual proof. Let's now take a permutation in Sn and have the transposition I, J in Sn. We have 2 cases. Case 1, where I and J are in 2 different orbits. And let's let our permutation be the product of disjoint cycles, where the first 2 terms are bj x, ai x, and the x's are just any other element that is in the orbit. So then the product of the transposition and the permutation is bjxx, which yields aj and now notice if they're in 2 different orbits, the product combines the orbits. So we now have 1 less orbit. And now case 2, we consider if I and J are in the same orbit. So this time let's have our permutation be, again, a product of disjoint cycles, but we only are looking at the first cycle where we have A, J, E, then the product of this will yield this. So if it is in the same orbit, our permutation will gain an orbit in the product. So now, again, we will look at the identity permutation in Sn. And as we said before, the elements in the identity permutation are in its own orbit. So this identity permutation has n orbits. And permutations can be composed by the product of its transpositions and the identity permutation. And we know that m cannot be both odd and even, because whenever we multiply a transposition with a permutation, we always gain or lose one orbit. And so if it's odd and we add another transposition, that will change the resulting permutation and change the number of orbits, which makes it not equal. And so it cannot be expressed as both odd and even. And that is our proof.